We're trying to assess the effectiveness of a treatment, let's say a new antidepressant drug. It's important to be able to tell whether the effect that we're measuring is real or whether it's due to random chance. Let's say that the treatment group experienced a better average effect than the control group. The improvement that they saw may have been due to the drug, but because we're dealing with a small sample that we're trying to compare and to be able to measure what's going on with the whole population, something else could be happening with this sample. And for the people in the treatment group specifically, maybe they had warmer, sunnier weather. Maybe they received good news or promotions at work. Maybe they happen to be drawn from a subpopulation that tend to be happier than normal. It could be any of these sorts of issues at play. To be really sure that there's a real effect that we're measuring, we can approach this using statistical tests. For instance, calculate how often one would get a difference as large or larger than the one obtained in the experiment if the experiment treatment really had no effect. Essentially, this is what we're doing with hypothesis testing. So to begin, let's define some terms. First is the null hypothesis. The null hypothesis is represented by H sub zero. That's H with a little tiny zero next to it. It's a hypothesis about the population parameter. The null hypothesis is that the difference between the means of each group equals zero, or that there's no difference between them if they're the same number. The null hypothesis is often the reverse of what the experimenter actually believes, but basically we put it forward so that we can use the data to contradict it. So for the example just given, the null hypothesis would be designated by the following symbols: H sub 0, mu1 minus mu2 equals 0, or by H sub 0, mu1 equals mu2. The other definition is the alternative hypothesis, H sub A or H little tiny a, or what the text calls H sub 1. The alternative hypothesis is that there is a difference between the two means. So we conduct our experiments or our statistical tests based on the null hypothesis, and that's what we decide on. We either reject the null hypothesis or fail to reject the null hypothesis. But typically what we're trying to discover, what we're curious about, is if the two means are not equal, if that makes sense. So once you get the hang of them, hypothesis testing problems are pretty straightforward. The first step that you want to do is define the null hypothesis and the alternative hypothesis. And this is going to be fairly simple. So the null hypothesis, H sub 0, is the difference between the two means equals 0. That's always going to be the case. And H sub A, or the alternative hypothesis, is that there is a difference between the two means. So that mu1 minus mu2 does not equal 0. Next, we select the significance level. Sometimes that will be done for us, so the problem will give us a particular significance level. Other times we can select it ourselves. We typically set the alpha equal to 0.05 or 95% confidence level. If we want to be a little bit more precise, we can set it to 0.01. But those are two of the most common levels that we choose. Now in step 3, we calculate the statistic that we're interested in. So if we're comparing population means mu in our hypothesis, then we would calculate the differences in the two sample means. From there, once we've calculated them, we calculate the p-value. The p-value is the probability of obtaining a statistic as different or more different from the parameters specified in the null hypothesis as a statistic computed from the data. And we compare that p-value to our significance level. If the p-value that we calculate is less than the significance level, then we reject the null hypothesis. That means that we are estimating a difference between the two sample means. If the p-value is greater than the significance level, then we fail to reject the null hypothesis. We don't say that we confirm the alternative hypothesis. We actually don't have enough evidence to do that. So sort of like in a court of law where we say guilty or not guilty instead of guilty or innocent, we just don't have the evidence to confirm that the sample means are equal. So we say that we fail to reject the null hypothesis. And the final step is simply to explain our findings. So we'd write down the estimates for the two means, the p-value, and how the p-value compares to the significance level, whether we can accept or we can reject the null hypothesis. Now, we're not always correct in our hypothesis testing. Because our significance level is, say, 0.95 or 0.99, there's always room for error, even if we perform all the calculations correctly and all that, just because we're dealing with samples. So they may not perfectly capture the population as a whole. So sometimes the sample mean that we draw from just doesn't represent the true population mean. Doesn't mean it's our fault. That's just what happens when you deal with samples. So we can divide errors into two types, type 1 errors and type 2 errors. With a type 1 error, the null hypothesis is true, meaning that there's no difference between the two means. But we reject the null hypothesis incorrectly. So we incorrectly find evidence that there is a difference between the two samples. So we find evidence of an effect or some sort of difference when there really is none. So for the drug trial example, it would be saying that we reject the null hypothesis, that the means are different. So we claim that we have evidence that the drug improved health outcomes, when in fact the drug didn't. There was no change between people that took the drug and people that did not take the drug. And we represent type 1 errors with the Greek letter alpha. Now, type 2 errors are the opposite. In this case, we fail to reject the null hypothesis, when in fact the null hypothesis is true. That's like saying there is no difference between A and B, when in fact there is a difference between them. So for a drug example, it's like saying the drug is ineffective, that the treatment group experienced no differences from the treatment group, when in fact the treatment group did have different outcomes. So type 1 error is an error in every sense of the word. This is much worse than a type 2 error. In this case, we say the null hypothesis is false when it really is true. So type 1 errors are generally considered more serious than type 2 errors for researchers or people working with statistics. But we have to be careful about trying to avoid type 1 errors too much. So there's a trade-off between type 1 and type 2 errors. The more we try to avoid the one error, the more of the other we get. So the probability of a type 1 error, that alpha, is called the significance level, and it's set by the experiment. So let's say we set the type 1 error rate, or alpha, lower. So instead of 0.05, we change it to 0.01. That reduces the likelihood of finding type 1 errors. But in that case, we make it more difficult to estimate an effect. So we risk increasing type 2 errors. Now, for researchers, leaning this way is considered better, but it's still a trade-off that we make.